And then situation 2, we put a little bit more time into that because we had some different ideas on what the position time graph would look like. Some folks were expecting it to kind of go like that, start out steep and get flatter over time. Some folks had it starting out flat and getting steeper. Some folks had it starting higher up the graph and then coming down to flat, or starting higher up the graph flat and then coming down to steep. But in the end, this was for the type of motion where the detector's here at the bottom and the card's going to get a little push. And so as soon as it leaves my finger, it becomes interesting. Oh, Christ. Looks like the Duke boys are in a heap of trouble. Make sure this thing's in the tracks. Just trying to make sure you're awake and with us. You got your dumb in, so you're good. All right, so I'm going to give this thing a push. And when it leaves my finger, that's when it's going fastest. And every little instant of time after that, it's getting slower and slower and slower until I pounce on it. It's got a velocity of 0. Velocity of 0 coincides with a position time graph that is flat. So that's what we see there. And then a difference with this one, again, the velocity is the slope on the position time graph. It starts out, and the key thing here, if you can draw the position time graph right and make sense of the shapes, you're going to be in okay shape. If you look at it, it starts out like that, and then at any other time in the motion, oh, don't do that to me, bro. I just want the blue thing. Never mind. At any other time, it's going to be flatter than that. So your velocity time graph starts out very positive, and then here at the end of this position time graph, it's flat. That's a slope of 0. That's a velocity of 0. The velocity graph is, again, a straight diagonal line. It's downsloping. It goes down as we go from left to right. So that is a negative slope. At any point along this graph, I've got the same. Wow, why is it not letting me do that here? I just want the little piece. Boo. Anyways, at any point along that graph, I've got the same negative slope. All those segments have the same negative slope. There we go. So if I go there, or if I go there, or I go there, always the same negative slope. That's why I always have the same negative acceleration. Okay? So the first model that we did this year was the constant velocity particle model. The things that move like this, where the velocity graph has a constant slope, these are constant acceleration particle model. Okay, or CAPM. That's what we're talking about here. So we went through what the graph shapes would look like for that stuff. All right. So that gets us up to speed with where we're going next. Situation 3. So the track's higher on the right side. The motion detector is down here at the bottom of the track. The cart is going to start out up here at the top of the ramp. I'm going to let go of it. It's going to become interesting when it leaves my hands. And then pounce on it right before it gets to the bottom. So what are those graphs going to look like? That is going to be no. Is this the right one for number 3? Speeding up, moving in a negative direction. Okay. So the pair deck is MERPM, MHRPM. Go ahead and join us over there. After you've thought about it on paper, some of the tricky things to be considering. the motion detector defines where 0 meters is. So here's 0 meters, here's 1 meter, here's 2 meter. Cart's starting here. Okay? Cart's going to end up, ooh, that was a dope rail slice, bro. All right? The cart's going to end up down here by the detector. So think about how that affects your graph shape. What is happening in terms of the speed of the cart, getting faster, getting slower? So think about how that affects your graph shape. Okay? But jot it down in paper, have a chat with your neighbor, and then slap it into the Pierre deck for us, please. Because now you're smiling. Look at that. Look what I did. I'm looking at your graph right in here. I see it.
Wait, what? Excuse me, did you say that was hers?
Oh.
She stole my Chromebook.
Well, bro.
Right when you looked up, she was like,
She's logged in.
You can do it.
She's got graphs in here. That's who it's logged in by. I'm going to take attendance later and I'm going to be like, oh, guess Eva wasn't here because she's not in the pair deck.
So then I might as well leave if we're going to count me on excuse anyway.
Or just pull it up on your phone.
This is my account. I literally just signed it with my account.
It says Kate Sayre right here when I look at it.
I don't believe that. Okay, but is mine, does it show you if you haven't drawn anything on it? Like, this is literally my Chromebook with my account logged in.
It literally says Kate Sayre for that set of graphs. Is that what the graphs are?
No, she has nothing drawn on this. She's just.
So she's on her phone? Or what?
No.
That works.
Stop drawing on my graphs.
Kiana, this is Abdul. Abdul is Kiana. She's the person that sits by it. You're making me feel like the worst person in the world. Talk to your neighbors. Come on. Come on.
I don't know what the answer is.
Oh.
So it's position time. So we'd be going down. Why? Because so it starts off at like 2 and it ends down to 0. So start up here and go down. Even though it's accelerating.
All right, we got some differing opinions on position time graph shape. So here's some things to talk about with your neighbor. Differences of opinions on where the graph starts and how the graph should be shaped. Be mindful that this is a buggy that gets slower or faster as it goes up the ramp. Be thinking about those things too. Oh boy. Well, what? That's your notes, bro. You want another copy of it? You bet. What is that guy doing?
She had lips in her hair.
Why do you know that?
Because I saw it on her head.
From that far?
Yeah.
Man, no wonder you're draining trays. She's got like that eagle eye. All right, so this is what it was. Here's what I see now when I look at these same three graphs. Now, there we go. Okay, so you can see the middle one changed. So now we're all agreeing on where this thing starts. Pretty much every one that I look at in there, you're starting high up on the axis. But then you got to think about the shape of the graph that you're drawing. Should it start out flat and get steeper? Or should it start out steep and get flatter? Watch the motion again. Think about when is it fastest and when is it slowest, okay? So I've given it a push. It's interesting as soon as it leaves my fingertips. And then I stop it up here at the top. When it's
going down.
Oh, crap. I was reading something different from that. Lo siento. Help me out here, Castor. What do I need to do?
Apparently it goes down.
Oh, I don't push. It starts out up here. That's why we all have it up there. It starts out up here. It's interesting when I let go of it till right before I stopped it here at the bottom. So when is it going fastest? That's when your position time graph should be steepest. So double check what you have and make sure you're in agreement with that idea. It starts from rest. That means its velocity is close to zero. That means your position slope should be pretty close to zero. And in the end, it's going very fast. Okay. So now we've got more of a consensus type look on the position time graph. Okay? Bruh. So position time graph wise, it looks like we're expecting, where do I want to go? I want to go here. It looks like we're expecting something that starts out up here, starts out flat, which is to say flat is just another way of saying slope is zero because velocity starts from 0 meters per second. Think about that. If I'm saying, I didn't have the thing where you can see the thing. All right. It starts out flat because we're saying it starts from a velocity of 0. Starts from rest. If that's the case, that's already telling us where this velocity time graph should start. Now, if you look at it right now, there's a lot of differences. There's not a clear consensus on where the velocity graph should start, but I'm telling you, if we're pretty much all in agreement that this is flat, that this is flat at the beginning, that's cueing you that the velocity should start from 0. And then have a conversation with your neighbors about what's going on here in terms of slope. See if you can think about what this velocity graph should look like. Starts with a velocity of 0.
Oh.
I'm trying to help you get rid of my face.
Oh, actually, what do you do?
Hold your ears, hold your fingers in your ears like that, and drink water like good, sustain 4 seconds.
It's just a one time. Wait, what does that do?
Was it?
It gets rid of your hiccups.
Yeah.
You can hold your breath.
Does that work?
No, it doesn't.
I go.
Well, yeah, but you got such amazing willpower. So.
Works for me.
Hey, how's my name?
All right. So velocity time graph, we're still in a bit of disagreement about. So here, let me give you a couple of pieces of advice. Remember, we drew that secant in the lab. I recommend you think about a secant for this curvy graph. So I'm going to put a dot at the beginning, a dot at the end, and I'm going to draw a line to connect those two dots. How would you describe the slope of that secant line? It's constant, okay? Also, what would you say about that secant line? Negative, is downsloping. That's cueing you that your velocity is going to be negative. So if you get a curvy graph, I recommend drawing a secant to help you think about, is this positive slope or negative slope? This secant's negative, so this graph has got a negative slope to it, negative general trend. So now I know my velocity graph is going to start from 0. I know I should be drawing it in the negative part of the graph because I have a negative secant for my position time graph. So I'm just a boy sitting here watching your pear deck, seeing if you can pick up on this and adjust your velocity versus time graph accordingly. Doesn't start out with a positive velocity. It starts out with a positive position. You're not graphing position on a velocity graph. You're graphing velocity. So it should start from a velocity of 0. And it should be in the bottom part of the graph. So there's kind of really only one way you can draw this thing. All right, now we're seeing some changes. So now we're losing those graphs that were in the upper part of the graph. And if you're going to start from 0 and you're going to be in the bottom part of the graph, there's really only one way to draw this thing. Okay? Ooh, and then somebody noticed this as well, right? It kind of cues you here. It's moving in the negative direction. Oh, now they're not cueing you. But they were telling you it's moving in the negative direction. That's kind of, okay, negative velocity then. So individuals, right? We still have some friends that have it in the positive. So somebody tap on those friends and make sure they're changing it. Still have some friends that are not starting from 0. Got another friend in the positive part of the graph. Sitting next to somebody else with the graph in the positive part of the graph. Boop. So in general, it looks like now we're expecting that for our velocity versus time graph. Wait, no, that's not a thing. Okay. So then, if the acceleration value is the slope on your velocity versus time graph, what is this telling you about the acceleration graph here? How should that look? All right, so let's go do some of this business. Position time graph. Let's see, cart's got to go down the ramp. I almost stopped it. So position time graph shape. This is going to start at about 1.6. It goes till just past 3. Let's say 3.1. And this doesn't need to be higher than 1.1. All right. So position time graph shape. Kind of like we said it would be. Okay, like a bottom opening parabola, or however Ms. Walker would say that. That's what's going on with the position versus time graph. Velocity versus time graph. Bruh. Where is it? What? Riley says it's negative. Ooh, so I don't need this part. Okay, so in general, for most of the motion here, the bit I've got grayed out, that's looking like a linear Negative slope, velocity versus time graph starting from 0. So then the acceleration versus time graph. The acceleration versus time graph should agree with your description of the slope here, okay? So take a moment, run it by your neighbor, but what words would you use to describe the slope of this red line? Weird. I'm not asking for anything more than a description of the slope of this line. Some of you are writing college entrance essays. All right, so over here on the Pierre deck, slope of the velocity graph is negative, constant negative, constant negative, constant negative, negative, negative slope, negative, negative. Okay, what you're telling yourself when you're describing the slope on the velocity graph, you're telling yourself about the value of the acceleration. So we should be drawing an acceleration that is constant and negative. And then when I go over into the actual graph that we made with the motion detector, and I change this to acceleration, during the section that I had highlighted where the velocity time graph was a negative slope diagonal line, we have acceleration. This top is 0 here. This is about -1 right here. So we've got an acceleration of about -1 during that window of time. So I'll throw another one into the pair deck quick. Do you have any questions, concerns, clarification you need right now? I'll just check in with you really quick in the pair deck. I'll see who's asking it, but when I share it with the class, it'll just be anonymous here. So something you're wondering, and maybe some of your friends are wondering it too. All right, so we do have a question here. Why does velocity start at 0? So for this motion, and I screwed it up when I was demoing it earlier. For this motion, I'm going to release this thing from my hand here, okay? So right now its velocity is 0. It's going to become interesting as soon as I let go of it. So at that moment that it starts, its speedometer is going to reach 0. By the end, it's going as fast as possible. That's going to agree with, oh, not happy. That's going to agree with this position time graph that starts out flat, and then over time it gets steeper, 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 steeper. By the end here, it's fairly steep negative slope. Why is the velocity going in the negative direction if it is speeding up? Run that by your neighbor really quick. Let's see if you can answer that question for that person. Why is the velocity going in the negative direction if this thing's speeding up? I like what you guys are doing here. You're thinking about this a little bit. At least some of you are. Jabril, I think you're using a German word there. I don't know what that is. I think you mean arrow, sir. Yeah, that a kid. All right, so what do we got here from our friends? Because the direction doesn't correlate with the speed. The slope on the position versus time graph is negative. Because it's going in the negative direction and velocity is an arrow, so it needs a direction. Because the slope on the position versus time graph is negative. So this is something that was kind of tricky from before. Sorry, and I didn't show you your friend's responses, but again, slope on the position time graph is negative. The object is going in the negative direction. The velocity is an arrow, so it needs a direction. Direction doesn't correlate with the speed. Okay, direction is just, is it going towards the detector or away from the detector? So if it's going towards the detector, you're going to be in the negative part of the graph. If it's going away from the detector, positive part of the graph. And then the other question, and I'm going to have you maybe come back to this one after we do section 4. Somebody wants to know what the difference is between the upward curve and a downward curve. Sometimes it curves up, sometimes it curves down. We want to try to think about what that's all about. Okay? To help us with that, I'm going to have you do the last one here. I think this is the last one. Number 4 says slowing down, moving in the negative direction. So I'm going to move the detector over to here. And I'm going to start the cart out down here at the bottom of the ramp. I'm going to give it a push. And I'm going to stop it at the highest point. Okay, so you're watching. Push, pounce. Okay, so think about, again, the detector is what is defining where 0 is. So we're kind of changing direction here. This is 0 meters now. Here's 1 meter. Here's 2 meter. Cart's starting out here. I give it a push. And I pounce on it there. So think about proximity to the detector. Think about when it's going fast, when it's going slow. Can you draw the shape of the graph? The position time graph. So again, I'm seeing like 3 different things. So please have a conversation with your neighbor about where should the graph start if the cart is starting out down here and the detector is up here. Okay? How should the graph shape start? How should the graph shape end for the position time? If interesting, after my push, And I can't keep it in the track today. If it's interesting, after I push it, until I pounce on it at the very top of its motion. Run that by your neighbor real quick. If you don't have a neighbor, get a neighbor. You're breaking my heart over there.
So I don't know, yeah, that's what I have.
Hopefully Shintaro is texting you from some other period.
Oh, you have it the other way.
But it's further away from that.
Running forward.
No, it just matters how.
How do you submit it?
It's just automatic.
Yeah, it just shows up. I'm just showing you 3 different examples to hopefully give you something to talk to your neighbor about. Should this graph start out flat, like the middle one, or should it end up flat, like the first and third one? Should it start out at 0 for the position, or should it start out away from 0 for the position? Okay? So think about all those things in terms of the shape of the graph that you're drawing. Because right now I'm seeing 4 different graph shapes for the position time graph. I need you to develop a consensus there with your neighbor.
I think it's the same thing. Yeah.
It's the graph.
Like 2 different ones.
Because what if the motion directed be positive?
It would be and then this one would be like up.
Yeah.
Oh, okay.
Right? Now I got 4 different answers. I've got curvy like that, curvy like that, curvy like that, or curvy like that. Like, have a chat with your neighbor, man. Help them out. Where does the graph start? We should at least all be in agreement there. If the detector defines 0, and I'm telling you the card starts out here, and it ends up by the detector. What's up? What's up?
So it doesn't start as zero.
No.
Nah, bro.
It's
Well, I'm just worried about position right now.
So the motion starts at is 1.0.
Which graph don't you like that you have there?
The positive.
I don't have an acceleration graph.
Then it'd be going
Oh,
down,
Lo
up like
siento.
that.
Okay, I don't really know what yours
Come on, take this.
Yeah, I'm more worried about position time graph right
I don't
now
know. I feel like it's
because we're nowhere near a consensus on position time graph.
starts at 0.
Yeah. So it'd be like the same one as up here. It would start up here.
I feel like this side would be. Well,
All right.
it's at 0.
I think if I look at all of them at once, I think there are very few that are like that. I can see 3 that go like that, but now it looks like most of them are going like that right now. Okay, most of them start out away from 0. And then, come on. It's going to start out away from 0, go like that-ish. So let's give it a look-see here. This is going to be a little bit trying
I'm confused. Is it-
on what the shape's going to be.
Well, I thought it was positive.
So here's my detector. So this is where 0 meters is. This is 0 meters right here. Here's 1 meter. Here's 2 meters. So can you see how I'm starting out at like 2 meters? I'm going to end up closer to 0.
Yeah. Oh, so it doesn't matter if it's.
As soon as it leaves my hand, it's going the fastest it's going to be going. Gesundheit. Try plugging your ears. No, really, it doesn't work for that. Okay, so it starts out, I probably should start this at like 1.4. Okay, starts out kind of steep And then over time, see how it kind of flattens out? Why is that? Run that by your neighbor. Why is it getting flatter here? What's happening motion-wise?
Like as it reaches the motion detector, it's slowing down to a 0 velocity.
So that's kind of where the consensus was as far as predicting the position time graph, that it would look like that. Okay, so we're good there. Velocity is based on the slope of the position time graph. Look at how this slope ends up. I'd say that's pretty flat. Flat slope. Here at the beginning, that's pretty steep slope. Ooh, if we do that secant thing again. In general, is this graph trending positive or negative? If I turn it into a secant, my secant's going to go like that. So think about what that's telling you. Where in the velocity versus time graph should you be? Right now, I crap you negative. It's probably equal number of that, equal number of that. So I really need you to have a conversation with your neighbor. Which one of these four is the velocity versus time graph that corresponds with that position time graph?
No.
No, I have it down as like 1.
Oops, that's not how this works.
Oh, I think it would be the top.
No, I'm warning you, bro. The secant is negative. That's telling you that this position graph is generally trending in the
Oh,
negative.
it would be the top of the start.
Let's call this graph A, this graph B, this graph C, this graph D.
Yeah, so they're different.
And we'll end with this. I don't know that this is ending with a win, but are you thinking A, B, C, or D there for the velocity graph? People are pretty much only voting for B or C. I don't have any votes for A. I have 1 vote for D. So if I get rid of A, nobody's expecting A. Nobody's really expecting D. So is the correct one B or C based on the position time graph's slope? I have it frozen. All right. So, hey, homework tonight while you're in the bathroom, think about which one of these graphs, B or C, goes with that red curvy graph, okay? Lab, staple it, put it in the red basket, make sure your name's on it. Have a great rest of the Monday. 3 more weeks of school this year. We can do this.